Welcome back. So we're doing the remainder of the integration sheet today. So I think this will be the last one. Well, one can tell. Alright, so we're looking for our dx, and we're looking for this idea that we've got a derivative somewhere in the expression that can be substituted out. So is there an f dash of x and an f of x? And if that's the case, then we're able to go ahead and make the change. So what we'll do here is we'll let everything underneath the square root sign become equal to 1 minus 3x cubed. And so we stay in the column using Leibniz notation. So we get minus 9x squared. Now the minus 9 is no good to us, but the x squared is. The x squared is good. Okay. Now the 5 can be isolated and taken out the front. So when we do this, we'll organise that. Now I'm going to allow you to work on doing the transpositions. Okay. So what we'll end up with is minus 1/9 u is equal to x squared dx. And this, my friends, is the purpose of u substitution. So are you there somewhere? Yep. Okay, you're gone. Are you there somewhere? Yep. There you are. So both of you guys are going. Okay? And you're being substituted by this. So we'll bring the minus 1/9, but remembering I'm going to bring the 5 down. So the 5 will sit on top as the 1, and so we'll have 5/9. That's just like 1/9 times 5, isn't it? Alright, so the next thing we want to do then is consider the denominator, because this numerator is now 1. And so we've got a bracket to the power of a half. And if we go one step further, we'll have a bracket to the minus a half. And what was in the bracket? U. So we're going to put U. This is now the trivial substitution minus half. So that's our line. That's where I hoped most people could get to. Now you're aware of U substitution integration. Alright, so if we do the calculus, up and under, plus C, then we've got minus 5. So, minus a half plus 1, it never goes away. Remember when I made a big fuss about teaching you from year 7? Well, this is why. It never goes away. Minus 1 plus 2 is just a 1. So we've got a half. Now, divide by a half is equal to times 2 over 1. So we're actually going to get minus 5 on 9. Instead of dividing by half, we're going to times by 2 over 1. And then u to the half plus c. And finally we're going to get minus 10 over 9 square root of u plus c. Okay, that's it. So that's our final result. Of course, remember you can even put those things in to complicated versions. Just to check if you want to. I've done this in the other part. So we're going to integrate quotient. So we'll better let Wolfie know we've got a bracket. So we've got 5x to the power 2 divided by denominator square root 1 minus 3x squared dx. And so it knows it's integrating with respect to x. And so that's the correct form of our integral. And so we've been able to produce this. Now, Wolfie's been a bit tricky. It's produced a simplified version. And Wolfie sometimes does this, doesn't he? He's introduced a couple of ideas there that related to the domain. So if we specify a domain, let's just see what happens with that. It might not do what I want it to do. No, it's still doing a complex value. Alright, so just thinking about it for a moment. Tick tock, tick tock, tick tock. I actually feel as though we're okay, although it's not giving me the best representation we want, because we're starting to move up in the world in terms of development. So we'll just have a look and see what it's done. It's taken the 5 off, that's good. Okay, so this now has been identified as a trig substitution. Now I did mention that in the map. Okay, I'm just wondering if I can go U substitutions. I'll just try a few things because it's worthwhile. No, it's still persisting in using the other substitution. So I'll have to just do a little bit of homework on how to get the correct substitution in. But nevertheless, it is possible to use a different type of substitution for this form of denominator, but that's not quite where we're headed yet. So we're happy just to have this on that part. All right, let's move on. Happy with that, so we'll go on to the next one. Okay, so what are the derivatives and what are the functions? Pre-work might help encourage you to recognise that this thing is sine x all cubed cos x dx. Now the differential of sine is cos, so even though it's in the brackets, we can let u equal sine x. Staying in the column, du dx then will equal cos x, and multiplying through by dx, du will be equal to cos x dx. Wow. So are you there? Yep. Are you there? Yep. So you're both substituted out for our simple du. So it doesn't get any easier than swapping du. Now, I can't impress on you the importance of being able to form your scaffolding to that point. Stay in the column. Okay, stay in the column, because that's what this is all about. This is all about staying in the column. And then, of course, the trivial one is that we've got u to the power 3. So u to the power 3, So now we can do the integration up and under. Look how simple that is now. That's been taken from quite a breathtaking integral to quite a simple integral, and it's simply up and under u4 divided by 4 plus c, and we can reinsert u. So we've got sine x to the power 4 over 4 plus c. And if you want to use the trigonometric convention of putting the power in the nest there, I'm happy to do that as well. Okay, but either one of those terms would be the correct answer. So more than happy for that. Okay, so it is possible to muck around with other forms, other substitutions, and so that is possible. Okay. If you get the substitution blatantly wrong, it might still be workable in terms of your use. But for this point here, I think I'm just going to leave it in that form. All right, so the next one we've got is 3 times the root 2 of 10. Now again, let's just put the 3 out the front and integrate to the power half 2 plus 10x multiplied by sec squared x dx. And what we find is that the differential of 10 is sec squared, so that's our substitution. So we can quite readily do that. So, what are we looking for? We're looking for let u equal 2 plus 10x, and staying in the column, two is a constant, so it disappears. 10x is sec squared x. This is another one of these wonderful things, multiplied by dx, and we get sec squared x dx. Are you there? The answer is yes. Are you there? The answer is yes. So we're substituting both of those out for du. We have the 3 out the front, and we have the trivial substitution, u to a half. So up and under, to do the integral, will be 3 times u half plus 1 is 1.5, or 3 on 2, divided by 3 on 2, plus c is equal to 3 times 2 on 3, the square root of u cubed, plus c, u was 2 plus the tan of x. So these are cancelling, and our final result is 2 plus tan x all raised to the power 3 plus C. So a fairly straightforward result if we do it that way. You could have left it as 3 on 2, could have left it as the bracket, could have been left as a bracket 3 on 2, but I've chosen to put the square root sign back in. So these are quite straightforward on some levels, but it's very important that you do your practice, please. Do as many as you can. Do your scaffolding. It's very important. All right, so the integral of 5 over. Now, if we need to do anything here, we've got a 1 over an x there. We've got a 5 we could bring out the front. So I might just relax this a little bit, bring this out, and this 1 on x, I'm going to bring it out as a separate product. It's under the bottom, so it's fine for it to sit like that. And then we've got the 1 because I took the 5 away. So it's a bracket squared, isn't it? And so what's in there is the ln of x plus 1 dx. So it's the same thing. So I'm going to let u equal the ln of x plus 1. And so staying in, leaving its notation, the ln of x, 1 is a constant, so it's gone. So the ln of x is 1 over x by differential, and so we get du is equal to 1 over x dx. Now, are you there? Yep. Are you there? Yep. You're both gone. You're both substituted out by du. So we can write du. This is the purpose of substitution. Okay? And then all we're left with is what's in the middle, 1 over u squared. Okay? So we can write that again. That's a much simpler integral to do, minus 2 du. Okay, so up and under means that we're going to get 5 u minus 2 plus 1 minus 2 plus 1. So it's going to be minus 1 divided by minus 1 plus c. So the integrand is there now. So we finally got that. Minus will interact with the 5 minus 5. And u to the minus 1 means that I can put u underneath, and u was the ln of x plus 1. So I've substituted it back in. U to the minus 1, 1 over u. We don't even write the 1 over u, so there's no need for brackets. Okay, so we end up with minus 5 the ln of x plus 1 plus c, and that's our final result. So it's important that you're able to manage these, please. Very, very important. Okay. What we're going to do here is think about how we would manage this one. There's a couple of different ways in our thinking or expression, and I don't like to make things complicated. In algebra, there's a whole bunch of stuff that you can do. Okay, you can make these seem very, very complicated. Okay, and there's no need to make it seem very, very complicated. There's just no need for it. Okay, the first thing I'll notice is that if I differentiate e to the 3x, because I'm now a wizard at the chain rule, I will recognise that differentially is going to be 3e to the 3x. Now, what I'm looking for is a derivative. So I do have a little bit of a problem up here in that I don't have e to the 3x by itself, but I do know about adding indices. So in actual fact, this is a bit easier than it might first look, okay? Because we can take the numerator and we can say e to the 3x, and by our rules of indices, we can say e to the 1. Now this is just like a2 times a3. It's just like that. I know. There I go again. Over here, we've got a5. But remember, it's a2 plus 3. So what I've done here is I've gone from this step backwards to this step. Okay, so that's all I've done. I've taken the e to the 3x plus 1, and I've turned it into e to the 3x, e to the 1. It's exactly the same. The concept is the same. So this now means that I've got an e to the 3x. Now that e to the 1 is just a number, so it can be taken out the front. So let's just keep going with this a little bit. Now put the square root into a half, and 1 plus e to the 3x. Now one more step. I'll put the e out the front and I'll bring the negative half up. So I've got e to the 1 integral e to the 3x times bracket minus a half 1 plus e to the 3x. Now, let's pre-work. So that was a lot of pre-work. So what we're going to do now is simply let u equal 1 plus e to the 3x. So when we differentiate this, stay in the column. Stay in the column. So this is a u substitution. So du dx will become, the 1 disappears, but this now needs a little mini one. And I'll just do it for the sake of it. M equals 3x. And u will be equal to 1 plus e to the m. The m dx, there's our little chain. And du dm, so there's our little chain. So what's 1 plus e to the 1? Well, 1's a constant, it disappears. E to the m remains as e to the m, that's the one we love. And 3. So we're going to put these back together as a chain. So we're going to get a final of 3e to the m, which is equal to 3e to the 3x. So that's a lovely little chain rule there, that we've had to use that chain rule skill. So this one now becomes 3e to the 3x. Now we want the e to the 3x but not the 3. So we do all our gymnastics. So we'll get 1 over 3 du is equal to 3e to the 3x dx. Now anytime there's a chain inside a u substitution, you're winning. You're Maths 1 champion. Okay? So this one, are you there? Yep. Are you there? Sorry, I've recreated that 3 when I shouldn't have. I have a habit of doing that, don't I? Leaving things where they shouldn't be. I've always done that. So e to the 3x, are you there? Yes, you are. So both of those are substituted out. They're no longer part of this formation. So we can put our substitution down now. Du gets rid of both of those terms. We have a 1/3, but we also have an e. So we'll put an e on 3. And that is our u substitution. That's what it's all about. Okay, being able to use the chain rule. You can see why I emphasize the chain rule so heavily. It must be done this way. Emphasize, emphasize, emphasize is how you do teaching, and this is an important moment. So you must be able to do your chain rule. You can't escape it, because when you come to do U substitution integration, this is the kind of thing that you'll need to employ. Your chain rule. It's very, very representative of Maths 1 and the skill level needed. Okay, so you must persevere and keep working, keep working. All right, so what we've done here is that we've managed to have just the bracket to the minus a half. So this is now the trivial substitution. So it's U to the minus a half. Okay, look at all the other bits around that make up. Okay, so the integrand is now going to become E on 3. Up and under is minus a half plus 1 is a half. U to the half, which is just the square root of U. And then we had divide by a half, which is times 2. 2 over 1 plus C. So finishing that off, we've got 2/3 E, 2/3 E, the square root of 1 plus E to the 3x plus C. So that's our final result. Okay, so that encapsulates all of the skills that you'll need, that I want you to have. You being able to use a U substitution chain rule within a U substitution integration. U substitution chain rule within a U substitution integration. And that'll mean that you're pretty much ready for Maths 1. Now, in all maths, there's a possibility of making different choices in the way that you unpack some of these. But that doesn't mean that that's rigorous. It doesn't mean that it's scientific. It just means that you're being a maths Olympiad. And to be perfectly honest with you, I minimise analysis to the point that it doesn't confound you, and the Maths Olympiad stuff I'm just not interested in. So those things are very important for you to get an even keel and to do things in a way that's manageable. All right, so let's see what we can do from here. And that's pretty much it. So I'll see you next time. Bye for now.